So it's always a pleasure being in Siam. I've been there many, many times, but this is today a quite special occasion because Oussama Hijazi is celebrating his 6 years birthday. And the first time I met Oussama was actually, I think, 1981. He confirmed this date. I had spent the year 1980 in the US, both in IAS, Institute for Advanced Study in Princeton, and then in the fall in Stanford. And actually, he came to me to do what one now calls a master thesis. And, but finally developed into a thèse de troisième cycle, which was what existed at the time. In France, there was not what one now calls PhD. There was thèse d'état and thèse de troisième cycle. And so that's the way we met. And actually, I must say that this period was an extremely exciting period from the scientific point of view for geometers, because there had been really a number of challenges coming from theoretical physicists. So this is the context I would like to describe a little bit, and how the various questions I've been discussing with Oussama and a few other people here in the room really came about. So just to remind you about a few of the key ideas or concepts which were really developing at this time. One of them was actually happening in Stony Brook, for the reason that C.N. Yang was in the theoretical physics department, and he tried, I was there in 72, 73, which was a very interesting place to be. In the department, there are 14 differential geometers, so it was Jim Simons who had built this group. And there was an attempt to really, physicists had the feeling that what they were doing at the time, which was gauge theory, really was requesting more mathematics. But I remember the first attempt was made while I was there in 1973 of this joint seminar between mathematicians and physicists, and it failed completely because the conclusion was what they were doing was in a sense in trivial bundles, and clearly there was necessity to have global point of view, but they were not ready for the global point of view. So, but it, of course, later on, not shortly after 74, 75, it really developed into something very important. So this was a time where a number of theoretical physicists really were looking into Yang-Mills theory, actually a twist of Yang-Mills equations, because it was really the Euclidean version of it. And actually many subjects became then very, very special. The absolute minimum of the Yang-Mills equation were involving the so-called self-duality equations for dimensions. Penrose had created this fantastic twistor transform, which would transforming these nonlinear equations into linear equations, provided you look at it in the right way in higher dimensions. And there were also at the same time, and for myself that's something I was trying to follow, some new developments in general relativity, many attempts of different forms to define a supergravity theory. And so if you look around for a number of topics that I've just been touching, actually for many of these questions there was hidden or very explicit the role played by spinors and the Dirac operator. So this is, in a sense, this was the environment intellectually which was really happening at this time. And clearly, it was a time still where the mathematicians were very much more, much further away from physicists than they are now. So in a sense, the two worlds were really different worlds. And there were a few people who were able to make the connection. So actually, as very often, so this is something that an old person like me can mention, to stress how important it is to meet people on some special occasions. Of course, you realize the occasions are special only afterwards, and that makes the necessity of being aware of these meetings. And of course, this happened to me, as I mentioned. I was in Stony Brook at that time. It was the first job occupied by Xingtung Yao, for example. Blaine and Marie-Louise were not yet in Stony Brook. They came later. So Jim Simons brought me to Stony Brook on that time. in his typical way, listening to a lecture by me in June '72. Next morning, I had an offer for a job, so it was a big surprise to me. I finally decided to go, but this year has been completely transformative for me. I spent the summer of '73 in Stanford at the invitation of Bob Osserman. That was also a very important moment because in the fall of '73 there was this special differential geometry summer institute of the EMS, where a number of things for global analysis came together. And somebody also who at this time actually influenced me quite a bit, although it was not obvious, was Sir Michael Atiyah. Basically, the place where I would meet him was the Arbeitstagung in Bonn. And just talking with him, he said, you must learn spinors, okay? And the person who actually brought me to spinors was Nigel Hitchin. He was doing his thesis at the time. You know, the title of his thesis is Harmonic Spinors, and he's looking at them in many different ways. So in a sense, that was my first encounter with spinors. It was a kind of a difficult encounter because it was not clear at that time how to look at them. If you look at the physics literature, it was full of indices everywhere, no intrinsic presentation. It was very hard. Of course, some people had understood everything and knew how to do it. Then I met also Blaine, was spending a year at the HES, '78, '79. And we had the interesting experience of I just went to him, it was late May. I was supposed to give a lecture for physicists. At that time, the importance of geometry to physicists was known. It was '78. And I just asked him, I wanted to get his feeling on more or less the agenda I had prepared for the course I was giving to physicists. And then along the way, we just discussed some of the questions that physicists were asking to mathematicians. And to my great surprise, I think to his great surprise too, we just noticed that for one theorem that physicists were looking for, he had the half, I had the other half. So it was in basically one day, the recognition, we had a quite decent theorem just without doing anything, just putting together two pieces. I should have spoken with him earlier in the year, which I didn't, but it just shows that you should not be too shy when you talk to colleagues. Anyway, somebody who really played a very important role for the problem I'm going to discuss is actually Isadore Singer. I spent, as I said, the fall of 1980 in Stanford, but somebody who visited me many times was Dan Friedan, who was at that time doing his PhD with Singer. And so I would visit Singer regularly in Berkeley, and part of the discussion was he wanted to be sure that Friedan was really moving forward with the PhD. But another part was something that puzzled him at that time, that one of his very good friends was Bruno Zumino, who is a theoretical physicist from Berkeley, who unfortunately died just last June. And one of the papers of Zumino is definitely using implicitly the way the spinors are changing when you change the metric. And Singer was uncomfortable with what Zumino had written. So I looked at this paper, couldn't understand it, or clearly there was even some points where I think there was really contradictions. So anyway, I knew this problem was around. It was supposed to be in a sense by Singer, so a priori should not be a too trivial problem. But I didn't know how to do it. And so my relation with Usama started this way. That is, I suggested to Usama to consider this question of dependence of spinors upon the metric. And he struggled to do it for some time. Then I looked at it, and I couldn't do it either. So I said, maybe it's not a good idea. So I wanted to check this with somebody who, as I said, introduced me to spinors, namely Sir Michael. And he said he didn't know how to do it either. Had no idea how you can do it. So I really considered this was just better to wait and to propose to Usama something else. And fortunately, I had met Thomas Friedrich, who had published his very interesting paper on the first eigenvalue of the Dirac operator and the new estimate on the eigenvalues. And then that's what Toussaint did. And as you know, this became the Hijazi inequalities, which you have been hearing about today. So this was the way we started, but I wanted to bring back this context of relations between mathematicians and physicists, and the fact that some questions which a priori are trivial sometimes get forgotten, because it's kind of strange that nobody looked at the question of dependence of spinors upon the metric. But then people try to do it their own way, and sometimes the own way is the wrong way. So at some point you have to solve the problem. So in a sense, that's what I would like to deal with today, and in the spirit of having a historical context. And so this summary of lecture is basically some basic facts. You have been hearing mainly lectures on spinors and Dirac operators, so you should consider this just as setting the notation. Then really dealing with this question of varying the metric. Then I will be speaking about killing spinors, because they come up very naturally if you look at the formula for the variations of the eigenvalues of the Dirac operator. And then a few comments on perspectives. But maybe some other people will have their own perspectives to add. So, okay, so I go very quickly. So just, as I said, it's more to fix notations than anything else. I will be working with a Euclidean vector space, which is going to be later on the tangent space to a Riemannian manifold. And you have the Clifford algebra, you have the twofold periodicity if you look at complex Clifford algebras. And so depending whether the dimension is even or odd, you have the Clifford algebra is simple, or the sum of two simple algebras. And of course the key point, these simple algebras are endomorphism of some vector space. And here are the vector space that I use, which are the notation I use for the vector spaces of spinors, which is sigma v. And of course, just by looking at the various, what I said about dimensions, the dimension is 2 to the n for when the space is either n equal to m or n equal to m plus 1. But you see that from this, of course, it's very clear where the metric enters in the definition of the Clifford algebra. It's much less clear how it enters in the definition of spinors. Because in a sense, you have this algebra. You say it's the algebra of endomorphisms of a vector space. But then what is easy to get is the projective space of this vector space, because that's basically the one-dimensional projectors of this endomorphism algebra. But to get really to the vectors requires some doing. It's not completely transparent. And so now, what are the spinors? So, of course, the spinors are the elements in these vector spaces. And of course, the key element, which makes them identifiable much more explicitly, is the fact that spinors are also vectors in a fundamental representation space of the group spin n, which is the universal cover of SON. And again, that's the way Cartan discovered them. He was doing a classification of actually the representation of the Lie algebra of the orthogonal group or special orthogonal group, and discovered that beyond the list of very well-known representations, there were some others. And in a sense, they appeared some kind of odd objects if you are systematic in the classification. They didn't appear as objects that you knew and you wanted to put them in a certain context. It just appeared because if you're really doing classification, you have to list all cases. And the key ingredient, of course, is what I just said, namely that the spin group is a double cover of SON, and with a kernel which is z over 2z as soon as you are in dimension 3. And the key point, of course, is to make the link with the Clifford algebras, just again I mean, that's, I'm sure, been said during this year. So the key point is to say that you can actually realize the spin group as a multiplicative subgroup of the Clifford algebra with a very specific property, because you want it to act on the vector space V. So it's the multiplicative subgroup which stabilizes the image of V, and with a certain normalization condition which really makes spin compact. If not, it would not be compact. And then the key point, of course, is that through this process you have an action of a group spin on the vector space. Now the question about dependence on the metric is, suppose you really insist on defining spinors without using the metric, what would you do? So in a sense, clearly you're using the metric if you reduce your group to the group SON, because to make sense of SON, you have to have chosen the metric. So you should just stay at the level of GLN. But the weak point, I mean, or the interesting point about GLN is that as a sometimes people say it's, from the point of view of algebra, it's a simply connected group, which of course it is not simply connected. But by this they mean that there is no finite dimensional representation of GLN which can be in the same way as you have to go from SON to spin n. Then if you want to go to the double cover of GLN, you have the trouble that there is no finite dimensional representation, which is not a representation of GLN. So in a sense, the group GL twiddle, this double cover, has the difficulty that it has no finite dimensional representation besides the one, of course, which go through GLN. And actually, this has been studied by physicists quite a bit. And the man who has published the most on this at this time, in the 70s, is Yuval Ne'eman, who is a theoretical physicist, both from Israel and US. And he really understood how to make it work, and he called them the objects of these living in these representation spaces, infinite dimensional Spinors. And actually, more or less, if you remember the theory of spinors, if you add up the spinors with the same half parity, then you get the Spinors. So you cannot isolate one type of spinors in this representation of GL twiddle n. You have to take at the same time the half spinors, the 3 half spinors, the 5 half spinors, and so on. That's why you call them the Spinors. You have to take a whole band. And for him, it was really a tool to really study what he calls the gravitational interaction of hadrons. So hadrons are particles which are subject to interactions which are of the type, weak or strong interactions. And so that was in his attempt to develop such a theory that he was doing this. And of course, he actually used a lot of representation theory, but of course infinite dimensional theory, which is the theory of Arichandra modules. So in a sense, this was in the physics literature already there, the idea that if you go away from the metric, then you have a certain price to pay, and particularly you cannot make sense of finite dimensional objects. You have to go to other objects. So in a sense, before moving on to really my topic, some general comments on the relation of spinors. So again, I mentioned it that the way they appeared in mathematics was not in themselves. It was just because you were doing classification and you had to list them in the whole list. Another thing which is very bothering for geometers, as geometers, we like to view things. And you like to view things as having a certain shape or a certain dimension. But spinors don't have a specific dimension. They mix things in a certain way. And this is, for geometers, sometimes something a bit bothering. But still, there is a very specific case where you can actually do things nicely, which is if you are not interested in a metric, but just a conformal class of metric. Then things get a bit simpler, and you know how to relate very easily spinors for two classes. And even Nigel Hitchin, in a very interesting paper called Linear Spaces, linear spaces of solution of certain differential equations connected to Dirac and so on, really shows how you can really make a construction for spinors which are attached to really a conformal class of metrics. So it has to, you have to play with the idea. If you twist, if you have some kind of a weight to the spinors, then you can actually make it truly conformally invariant and not just conformally covariant. So this is something which were my comments on spinors. So of course, if you want to do geometry, doing the algebra is not enough. You have to go to bundles, and you have to work over general manifolds. And of course, this didn't happen so easily. And the first point I want to make is that there is, of course, for the theory of spinors, a very important book which was published by Élie Cartan in the 30s. And actually, in this book, the very last statement is a very interesting one because it really probably blocked a number of people for a number of years. It didn't block Élie Cartan at all. He hadn't understood things exactly well. So he just says, this is the statement, the very last statement of the book. The difficulties that one encounters when dealing with spinors in the general context, that is to have it on a manifold, are unsurmountable if you insist on using the classical technique of Riemannian geometry. So the key point, of course, what does he mean by this? He means by this that just because of the fact that spinors make sense only if you have fixed the metric, as soon as you want to use general coordinate transformation, then you cannot move spinors. So you are in difficulty. And of course, in his case, you know, he has been using his moving frames, and the advantage of moving frames, they were really orthonormal frames. So therefore, in his context, using spinors was not a problem. But actually, this was not understood. And there is an interesting article by Leopold Hennenfent, who was one of the physicists working with Einstein. By the way, if you're interested in somebody who had a very complicated, difficult life in many ways, it's a very interesting life to look into. But anyway, Leopold Hennenfent, of course, was very much interested in general relativity. And of course, if you are serious about doing variation, I mean, using variational principles in general relativity, of course, you need to vary the metric. But if you vary the metric, you vary the spinors. And so how can you have a variational principle based on spinors when you don't know how to compare spinors from different metrics? So actually, he says that maybe you should not do that, and spinors should be fixed in some kind of a Minkowski background metric, and then you use them as with this background metric. So it was clear that these comments by Cartan actually influenced people negatively, in the sense that people were afraid of doing this in a general context. And actually, if you look at the article by Yuval Ne'eman, he takes the pain of not only working with GLN and GL twiddle n, but also looking at the group of diffeomorphism, which is, of course, the group acting when you make coordinate changes, and, of course, looking at the double cover of the group of diffeomorphism, which, again, is a very abstract object. You cannot just realize it so easily. So this question of for benders as for spinors to have to understand the behavior when you change the metric in general was really there. So, of course, if you want to generalize, to have spinors on the manifold, the language of principal and associated bundles is the key. And of course, you do that by doing the usual construction with the group ON or SON, and then you have to lift it to the group spin n. And of course, you know, when you want to extend the group like this, then you may have a topological obstruction. And the topological obstruction, as you know, is the second Stiefel-Whitney class for the tangent bundle. I'm here dealing only with the case of the tangent bundle. And therefore, the setup is quite easy now. You take a principal bundle, which is under the group spin n, covering the bundle of orthogonal basis. And so this choosing this bundle determines the spin structure, and then you use the usual classical associated bundle construction to get the bundle of spinors, just as the associated bundle to the principal bundle using the standard representation of spinors. And then a spinor field is a section of the bundle of spinors, and the bundle of Clifford algebras makes sense in all the time without any restriction, but then you can have it acting on the bundle of spinors. And now the key point to do geometry, of course, is you want to be able to compute derivatives of spinors. And if you look carefully and think a little bit, you realize that the nice principal Levi-Civita connection form on the bundle of orthogonal frames actually lift nicely to the principal bundles of spinorial basis. And then you can extend and get a covariant derivative operation on the spinor fields. And therefore, as soon as you have all these tools, it's very natural that you look at what kind of differential operators you can define on spinor fields. And the key element to understand this is, of course, if you look at first-order operator, the principal symbol should be an equivariant map from the cotangent bundle tensored the bundle of spinors into where you want to go. So actually the key point is to know how you decompose under the group spin the tensor product of these two spaces. And then if you realize that you have exactly two components there, the natural bundles, which the maps which give you these the projection from T star M tensor sigma M to sigma M and sigma 3/2 M give you the two operators. So the first one is, of course, Dirac, the Dirac operator, which is obtained by projecting T star M tensor sigma M to sigma M. And there is another one, which is the twistor operator that you obtain by projecting to sigma 3/2. So these are, in the sense, strictly from representation theory, the two universally defined operators on spinor fields. So these are the situation, and now, so I go very quickly there. You know all the very critical, important properties of the Dirac operator. The reason why it was introduced by Dirac, it's a square root of the Laplace-Beltrami operator in the Euclidean setting. Dirac was working in the Minkowski setting, so of course it was a square root of the wave operator. That was exactly why he introduced it. And then, of course, in the Riemannian setting, Dirac is elliptic. The principal symbol is given by Clifford multiplication. It is self-adjoint operator, and there is the famous formula, which has been repeated here a number of times, which is the Schrödinger-Lichtenowitz formula, which relates the square of Dirac to really the covariant derivative with this extra term, which is the scalar curvature. Okay, so let me come to my topic, which is really varying the metric. So varying the metric, there are various sides to this question. So the first one is algebraic. That is already we should be able strictly in an algebraic context to take into account that you change the metric. And of course, if you want to do geometry, there is another one, which is when you move to manifolds and in a Riemannian context, that is with a metric whose the values of the coefficients vary from one point to the next. You really want to really have time to, have the tools to deal with that. And so to make this description, I had two possibilities. Either use the initial thing that I did with Paul Gauduchon, and which we published in French in the Communication Mathematical Physics, which was kind of a challenge, in 1992, which was the end point of several years of discussions. So more or less, we got the formulas quite clearly in our hands, something like 1988 or 1989. Took some time to get it done. I could have been following another approach, which actually is much more elegant, by Christian Beer, Paul Gauduchon, and Andrei Moroianu, which they published in 2003. I don't know exactly when they got it, maybe 2 years before, or I don't know exactly. And in the article, which is entitled Generalized Cylinders in Semi-Riemannian and Spin Geometry, it's not only more elegant, but it allows you to really deal with Lorentzian metric, which, for all the reasons I explained, is not a minor thing, because you really want to be able to use these tools in the context important for theoretical physics. But also, in their paper, they published some important geometric theorems. Actually, there is one point I want to make too, which is, I couldn't find again the exact reference, but some people have been trying to generalize what Paul and I have been doing in the Lorentzian case. But I know two papers which had been published on this, which I personally find incorrect. So I think it was needed that somebody came up with a good solution to this question. And so the setting is the following one, which the first time you think of it doesn't seem completely obvious. That's why we got stuck for some time. Is you take two metrics on a vector space. So in my case, Euclidean metrics, but as I said, general metrics should be considered also. And the key point, of course, if you think geometrically, which you should have, is to have some kind of a natural correspondence between the orthogonal basis for the G metric and the orthogonal basis for the H metric. And okay, so how do you do such a thing? And actually, one way of looking at it, which I think is quite useful, is to think of a basis, a G basis, as just a linear map from a model space, Rn, in which there is a canonical metric, the standard metric, to the vector space you are interested in such a way, so you think of a basis as some kind of a way of naming n vectors from the natural vectors of Rn, so that when you pull back the Euclidean metric from Rn to V, then you get G. Okay, so this is one way of thinking of a G orthogonal basis as a set of invertible maps from Rn to V with the property that they behave with respect to the Euclidean metric on Rn and the G metric on V in this way. And of course, it's trivial to make the comment that if you look at the other G orthogonal basis, they can be obtained from this basis seen as a linear map just by letting the group, the orthogonal group, but the orthogonal group of Rn act on the right. So if you compose at the origin the linear map with a transformation like O, then you can actually get all possible orthogonal bases. And so now the important object to introduce, because now I have a second metric, H, and now I can transform this metric, this bilinear symmetric to tensor, into a linear map by using the metric G. So G is a metric, so it has an inverse. And this inverse, of course, is an object which is twice contravariant. And so if you contract the twice contravariant object with H, you get something which is the mixed, which is an endomorphism. So of course, this capital H sub G is a linear map from V to V. And of course, by definition, if you evaluate the bilinear form HV on V1 and V2, it's exactly the same as evaluating G on H sub G of V1 against V2. So this is just the very definition of HG. And now the correspondence I was looking for, I said I want to create a natural correspondence between G orthogonal basis and H orthogonal basis. It's just the following one. You take a B that I think has an orthogonal basis for G. So remember, I think of it as a linear map from Rn to V. I just compose on the right with Hg to the -1 composed with B. And so the equivariance under this action of the orthogonal group is obvious by the very construction. And so this is the way you end up. So of course the only question you may have here is that what is this business of taking the square root? Can you really take the square root? And of course there the fact that Hg is a positive definite, that it comes from little h, which is a positive metric, of course, is very critical. Okay, so this is the way you create this map between G orthogonal basis and H orthogonal basis. And so, of course, now we want to go to the bundles. And so, in this case, we want to be in the spinorial setting on manifolds. So one needs a bit more geometry for this. So, of course, we have this natural bundle from what I call the invariant, invertible linear maps from Rn to V. I told you that I want to think of a basis of V as such an invertible linear map. And I can, of course, map it to met V in a very obvious way, because, as you know, if I have such a linear map, I can really pull back the Euclidean metric under the inverse of this map and get a certain metric on V. So this is the map which goes from invertible map from Rn to V to met V. And of course, if you take for any element there, the tangent space on the space of invertible maps from Rn to V is just linear maps without saying that they are invertible. So it's in a sense a space of matrices because it's really a linear map from Rn to Rn. And now the key point is that of course, if you look, so I introduce my map from invertible map from Rn to V, a basis, to metrics. And of course, if you look at a given point, that is a given metric, what are all the bases which sit over for this map over this metric G are exactly the G orthogonal basis. And so it's very clear that from my construction, the subspace, which is made of the images of symmetric matrices, is exactly transversal to the projection I said. Because tangent to the space of orthogonal basis, of course, I have the skew symmetric matrices, not the one. And I'm in the space of all matrices. I have a subspace, which is the space of skew symmetric matrices, and of course, orthogonal to this one in a very natural way. There is a space of symmetric matrices. So now we are in a business we start to like as geometers, namely you have a bundle, which is the bundle of invertible map from Rn to V, mapped onto metrics. And then you have a certain horizontal space with respect to this projection. And of course, if you have to check, and that's an easy check, that this gives you actually an ON connection, because you have ON acting on the fibers, but actually it moves the horizontal space onto each other. It's just a very trivial verification. And of course now, suppose you give yourself a curve downstairs on the space of metrics, joining two metrics, Then you can, so I gave an example, the typical segment in this space of metrics is as a convex structure. You can really build convex combinations. Of course, you can now lift horizontally this curve. So from a curve in the space of metrics, you can create a curve between bases. So that's exactly the key point. And of course, by construction, if I start from at the point G downstairs, and I lift upstairs, I'm starting from a point which is an orthogonal basis for G, and if I follow my path and follow horizontally, I end up at an H orthogonal basis. So it's interesting that you have constructed in a very natural way, that is without making any choice, but the obvious choice of saying that symmetric matrices are perpendicular to skew-symmetric matrices. Then you have created a way of associating to any G basis, G orthogonal basis and H orthogonal basis. And actually, if you do the calculation of using this convex combination, you end up with the formula I told you. So in a sense, the formula I propose, which you can guess as something which should be natural, actually it's not only natural, it's something which you can get by a homotopy procedure. And having this lifting procedure is of course very important if you want to do geometry. Implementing the algebraic formula geometrically was not so useful actually. So in a sense, what I just said provides you with a new definition of the correspondence I have introduced before. And of course, because I've been doing lifting, now if I go back to my context of geometry, which I have a manifold, I have a metric on the manifold, actually two metrics, two Riemannian metrics, G and H. If I put myself at a given point, above this point I have the bundle of a G orthogonal basis, I have the bundle of H orthogonal basis. They all sit inside the equivalent, the analogous of the invariant, the invertible maps from Rn to the tangent space at that point. And then using my lifting procedure, I can really create now a process by which I can really lift upstairs and get a correspondence from G orthogonal basis to H orthogonal basis in a completely natural way. And of course, this advantage of this is, of course, my procedure, which I did over orthogonal basis. Now, suppose I've chosen the same spin structure for my, so now I introduce two spin metrics, which I call gamma and eta, corresponding to G and H. Of course, if I'm using the same spinor bundle, but of course, two realization, one for the spin and principal bundle for gamma, the spin and principal bundle for eta. Actually, what I had been doing as correspondence between G orthogonal basis to H orthogonal basis, I can lift it up to, provided I'm using the same spin structure, I can lift it up to the spinorial basis. And of course, since I've done that on the spinorial basis, my correspondence, I have also a correspondence between the bundle of spinors, for the gamma spinors and the eta spinors. So this is the process. Actually, again, I mentioned that earlier, if you have just conformally related metrics, you don't have to work so hard, and you just use the fact that if you have the proper weight, actually you can, it's just a matter of putting the right weight to the various objects, so it's very simple. And of course, there is one step further, which makes life a bit more complicated, is that you want to, I stress that as soon as you have a spinor structure and a spinorial metric, you have also a natural covariant derivative. But now I'm using two different spinorial structures, gamma and eta, and of course they have different covariant derivatives, the one coming from G and the one coming from H. So now you still need to compare those. And in particular now the key point is that you want to compare the Dirac operators. So now the difficulty is that on one hand, if you're looking at the Dirac operators for gamma, it acts on gamma spinors and map them to gamma spinors. But if you are looking at the eta Dirac operator, it maps eta spinor fields to eta spinor fields. So in a sense, to make good sense, to compare the operators, it's better that you compare them acting on the same space. So that's why the only way you can actually do that is created what I call here a transmuted Dirac operator, which does the following. So you have your eta Dirac operator, you want it to act on gamma spinors. So the only way is to move the gamma spinors to eta spinors, act with the eta Dirac operator, and then move them back to gamma spinors. So that's the transmutation. So still, of course, the new operator is an operator which involves, which acts on gamma spinors. That was very critical if I want to compare. But the price to pay, it's very easy to see that this new operator is not anymore a gamma spinor, for the reason that, of course, its principal symbol was the Clifford multiplication of the other metric. So it's not the same as the one we had. But it's still a differential operator of order 1, and we can compare them. And so you can really, I'm going to be interested in first order variation. You can do a more general theory, but here I'm in particular interested in computing first derivatives. So if I want to compute first derivatives, it's enough to look at the deformation of the metric, which is very simple. That is, you just take the metric you start with, and you deform it by adding t times k. K is symmetric to tensor field, and of course, t is just a parameter. Of course, I could take a general curve, but of course, the only first derivative at t equals 0 would matter for the first variation. And so the theorem we obtained with Paul is the fact that if you look at the derivative of this family of the transmuted Dirac operators, of course, I bring all the Dirac operators along the curve gamma t, which is lifting, which is the spinor structures, the spinorial metrics attached to GT, and we all bring them back to the gamma spinors. So you get a quite involved quantity, which, so again, I'm using this notation capital K sub G, which means I'm transforming my symmetric to tensor field little k into a linear map using the metric G. So this is the formula you get, which is what you get. You cannot change it. That's life. And of course, from that on, you can really do one more thing, which is to study the variation of the eigenvalues of the Dirac operator, which is clearly something of geometric interest. And so you can do that. And so let's suppose we put ourselves in a simple situation. Let's assume the manifold is compact, because I will have to integrate something in some sense. So I need to integration to make sense. You can also add appropriate decay conditions if you want to do things on non-compact manifolds. And of course, there's always, when you look at variations of eigenvalues of operators, the difficulty that when there is some multiplicity in the eigenvalue, then of course by a variation you can blow up the multiplicity. So let's look at the simple case. You can actually do the general case, of course, provided your deformation is analytic. You can really assume that the eigenvalue is simple. So here is the formula you get. The variation of you fix a certain eigenvalue, lambda of the Dirac operator. Then the way this eigenvalue vary, when you vary the Dirac operator, is given by the integral over the manifold of the scalar product pointwise of the infinitesimal variation of the metric. You expected that. I mean, that's the whole game of looking at first variations. Again, a certain very specific symmetric covariant to tensor field, which I denote by Q sub psi. So how do you evaluate it? When evaluated over, so psi, of course, I should have said it, is a unit vector in the eigenspace for the eigenvalue lambda. So it's a quantity which is directly linked to lambda. So it's given by this formula, 1/2 real part of the x Clifford multiplication with gamma of the covariant derivative in direction y of psi, plus the symmetrization in x and y. And you just take the real part of this. So as a quadratic form, you see that it involves x dx psi times psi. So it's an interesting object. So this is this object, and actually it's interesting to discuss various aspects of this. So the first one, which is very natural, is the fact that it's obvious that eigenvalues of operators, natural operators like this one, are invariant when you replace the metric by a diffeomorphic image of it. That is, if you take your metric, just take a diffeomorphism phi, and just take phi star of g, just the image under phi of the metric, the eigenvalue is not going to change. It's a scalar. So how can scalar be affected by a diffeomorphism? And so the key point is that you remember the formula for cube psi. This is reflected in the fact that the cube psi is actually divergence-free, provided the psi is an eigenspinor. So the reason why you have this property is a very usual property when you are dealing with deformations of metrics, namely this cube psi as a tensor field has to sit orthogonally to the tangent subspace of the tangent space to the space of metrics at G, which consists of Lie derivative of G with respect to the vector fields. If you take one parameter family of diffeomorphism and starting from the identity, so you have a curve T goes to phi sub T star of G, then of course when you compute the derivative at T equals 0 of such a curve, which a curve, of course, is moving in the orbit under diffeomorphism of the metric, you get exactly the Lie derivative with respect to the infinitesimal generator of this family of diffeomorphism of the metric. So, of course, for every such symmetric tensor field tangent to the orbit under diffeomorphisms, of course, the variation of the eigenvalue should be 0. And therefore, it means if you integrate by part, because it's the Lie derivative of the vector field, so you move the derivative to the cube psi, then you actually are in the situation of having the integral of any vector field against the co-differential of cube psi should be 0. So it shows that cube psi should be divergence-free. And another point, which is an easy comment, so if I go back to the formula for cube psi, it's very clear that if I take the trace with respect to the metric, so if I sum up for an orthogonal basis at any given point, so I replace x and y by EI, and a G orthogonal basis, look at what happens. I'm just looking at the scalar product of Dirac applied to psi against psi. But psi is an eigenspinor, so it goes out. Lambda, the eigenvalue, goes out, and just have the norm of psi squared. So this is what I say. The trace with respect to G of cube psi is always lambda psi squared. And it's clearly non-negative as soon as the eigenvalue is non-zero, and even more than non-negative, it's actually positive almost everywhere. Because, and now, of course, it's a very natural game to play, which is to look for metrics for which a given eigenvalue is critical. And the typical case where this happens is the case where for the metrics admitting so-called killing spinors. And I just want to finish by talking about killing spinors, because again, it's a very interesting story on how a quite important notion comes up somewhere and actually proves itself to be extremely useful elsewhere, and even when translated into math, gives rise to completely different mathematics than it was expected originally. So killing spinors. So let me remember I introduced two operators, the Dirac operator and the Penrose operator, as the only universally defined differential operators in the context of spinorial geometry. So what is a killing spinor? A killing spinor which is at the same time a spinor which is annihilated by the Penrose operator, so it's in the kernel of P, and at the same time an eigenspinor for the Dirac operator. And the characteristic equation, if you remember when I presented the Penrose operator, you just introduced the idea that it's an eigenspinor for Dirac. So this is the equation you have, which is first time you look at it, very strong equation, because it says it relates very directly the value of the psi at any given point with its covariant derivative in any direction. So this is a very, very strong system. It's an overdetermined system. And actually, why is it called a killing spinor? It's interesting, and that's the way Penrose introduced it. It's kind of interesting. So because if you look at the one form on acting on vectors on the tangent space, which is obtained by actually looking at the component of psi tensor psi bar sitting in the one. So you see, remember, the spinors are elements typically which it's a vector space whose space of endomorphisms gives the Clifford algebra. But the Clifford algebra looks very much like the exterior algebra. So if I take a spinor field, tensor it with itself, actually with its conjugate, because I'm here working with the complex spinors, I'm getting something which actually can also be seen in the exterior algebra. So it has components. Of course, the obvious component in the zero form is just a norm squared. if you look at the component in the 1 forms, that's the one I'm considering, but you can also look at the component in the 2 forms, 3 forms, and so on. So here I'm looking at the component in 1 forms. And actually, from the equation of the killing spinors, if you form this psi sub psi, it's actually automatically a killing vector field. So you can think of a killing spinor somewhat as a square root of a killing field in some way. Typically, it's a quadratic quantity which gives rise to killing fields. And actually, the other components, I'm looking at I spoke about the norm squared, I spoke about the 1 form, but you can also look at the other components. And it's very interesting. The reason why Penrose introduced that, he was looking for first integral for the geodesic flow for some very specific general relativity models. And he just understood that by introducing such a psi, you got many scalar first integral for the geodesic flow, which actually allowed him to make the flow integrable, which was very interesting. So that was a motivation, which was kind of a side motivation considered what the killing spinors have been playing later on. Because now they are actually now very extremely directly connected to supersymmetry in a way which is very interesting. That is, supersymmetry is an attempt by physicists to insist that actually this dissymmetry, which is usually seen between fermions, which are living in the spinor world, and bosons, which are living in the tensor world, there should not be this dissymmetry, and there should be transformations which map one to the other. First time you think of it, you are very surprised, because they look very differently. But anyway, the possible formulation of such a supersymmetric context is that there should be supersymmetric transformations, and actually killing spinors should play the critical role. They should be the ones which you take a spinor and you map it to an object which is a 1 form by the transformation I've written there, using a psi, which is a killing spinor. So that's the formula. And of course, as soon as there is a killing spinor, because I told you this equation is overdetermined, there are very strict conditions on actually the Riemannian geometry of such an object. Actually, if you compute the curvature of the bundle, you get a very nice formula, which looks like the curvature is very simple. And one of the consequences of this, that's automatically the space is an Einstein space. And if you're looking at the compact setting, lambda is necessarily a real number, eigenvector of eigenvalue of Dirac. It shows that the Ricci curvature has to be positive. Of course, if you allow for, if your manifold is non-compact, you may have lambda purely imaginary, and then, of course, you may have Ricci negative. And so this classification has been going on with classification of the value of lambda. Of course, if lambda is 0, then you will go back to the equation I showed you. It shows that the killing spinor is actually a parallel spinor. So in this case, it's known that the autonomy has to be reduced. Of course, if it's purely imaginary, the manifold is non-compact, and if it's real, then the manifold has to be, if it is complete, then by Meyer's theorem, it's you can really describe the manifold. And the key construction to study killing spinors, physicists have been struggling with these killing spinors. They had very explicit examples of such, and they didn't know how to, they had many conditions and so on, they didn't know how to discuss them. But Christian, who is here, just made the breakthrough, which is to relate your manifold to another object built over it, which is a cone. And if you endow the cone with a very simple metric, which is a cone metric, then the good surprise, if you have to make some identifications, you can actually map the spinor fields on the basis of the cone into spinor fields on the cone. And then the good surprise is that the killing spinors on the basis of the cone generate actually parallel fields in the cone. And of course, parallel fields, you are comfortable, you have reduced autonomy, and you start to discuss things much more comfortably. And so this has led to very interesting consideration. There are many people here who have contributing. And there was first classification for the ones with parallel spinors having reduced autonomy. And many people have been discussing this. And it really led the very interesting cases of spin 7 and G2, which were eluding all. There were no examples for a long time. There was not so sure they would exist. And so anyway, so now we have plenty of examples, and this construction has helped. In the case of non-compact manifolds, Elga Baum gave a nice description, which uses a lot of hyperbolic spaces and warp products. And of course, actually, one can almost completely classify them. In the case of standard sphere, the standard metric, the bundle of spinors, is actually trivialized by killing spinors in a very simple way. Namely, you take the, what is the cone of the sphere? The cone of the sphere is just Rn plus 1. So you take the parallel spinor in Rn plus 1, you restrict them in the proper way to the sphere, and then it gives you exactly what you need. And actually, there's discussions of possible, when you can have possible examples, and in the only exceptional dimension in this context is dimension 6, and actually you have very nice connection with the so-called nearly Kähler metrics, and which are non-Kähler. So that's a very interesting situation. And of course, there are many other examples, so I don't want to be too long on this, and related to a number of extra structures which have been discussed actually in the previous lecture in some way. And so I'm more or less skipping this. Because it has been discussed quite somewhat by some people in this lecture, and several experts are here in the room. The example I want to spend more time on it is the so-called squash 7 sphere, which actually for the physicists was a great motivation, because it was one of the situations where they really could connect this to supergravity in a very efficient way. And what is very interesting in this case, that it's not in the standard sphere. Of course, you have this property that, as I said, the bundle of spinors is parallelized by killing spinors. So there are plenty of killing spinors. But in the case of the squash 7 sphere, it is obtained by a construction which, of course, is very appreciated by geometers. Namely, you remember that the 7 sphere fibers over the 4 sphere with fibers S3. And if you uniformly squeeze the S3s, actually it was discovered that for a proper squeezing, you actually get another Einstein metric on the 7 sphere. And you remember I mentioned that if you have a killing spinor on the manifold, it must be Einstein. So actually, this Einstein metric obtained by squeezing on the 7 sphere is exactly one where you have one killing spinor, but you don't have more, you just have one. And it has been really discussed in great detail by physicists as a very good possible setting for discussing, supergravity. And supergravity, was always constructed as an 11-dimensional story where you have space-time for 4 dimensions and something else for 7 dimensions. So this was the 7 dimensions. Anyway, so I'm finishing with some perspectives, short ones. I'm sure you will have others. So I think what the lecture was about is to show that although spinor fields or spinors in general are quite subtle objects, they play such a fundamental role in theoretical physics that they must be studied very, very thoroughly. I mentioned that it took a long time for mathematicians to take it seriously. It's really the work of Atiyah and Singer on the index theorem, which I've skipped in my lecture, which I could have mentioned, of course, which made them really so central in mathematics. And in particular for the reason that you can generate all principal symbols of elliptic operators using Clifford multiplication, using Dirac. And of course, there have been several good documents to really make propaganda about Dirac operators and spinors. The first one were the books by Élie Cartan, although clearly they were misunderstood partly. There were, of course, then the very critical book by Blaine and Marie-Louise, who has played a very important role to educate us in many different ways, including the topological side of things. And now I think some progress has been made, so mathematicians feel more comfortable with the spinors, and they really play a very important role in mathematics. And I'm sure you have been hearing during this conference a number of such contributions to the development of the theory of spinors and Dirac operators in mathematics. Nevertheless, it seems to me that you have not yet completely reached the full potential of the theory. So where should this come? So first of all, I'm repeating something which was told to me by André Lichnerowitz, which is that to understand Einstein metrics in general, one will have to understand spinors. So he was repeating this in a number of ways. And I will right at the end of this page, which is my last transparency, really comment on something which goes to, really points to the same direction. But anyway, I think there is still something to be done, which I've tried a lot without success. So we should keep trying. But I'm sure some brighter people will make contribution in this direction. And one thing I want to stress also is that, you see, mathematicians have really focused their attention on spin 1/2 objects, what we call spinor fields. For physics, it's not correct to limit your attention to 1/2 spinors. You really have to consider more general spinors. And the next level of spinors are the so-called 3/2 spinors, the next thing, which is one of the irreducible components, as I described, when you make the tensor product between the cotangent bundle and the half spinors. And there is a very natural operator, which plays the role of Dirac there. What you have to do then for natural operators on 3/2 spinors, you have to take the tensor product for T star M with the 3/2 spinors, and no surprise, you get something which are the 5/2 spinors coming up. And so this actually could be connected to what physicists call gravitinos and so things of this sort. So I think this very specific operator, which is called the Rarita-Schwinger operator, has to be studied, and it has not been studied so much by mathematicians. It's a mess, in a sense, so don't be surprised. I mean, if it has not been studied, it's also because it's not so easy, technically. I mean, maybe if we look at it in the right way, one should be able to do that. And my last word would be about a paper that Bernard Julia has been writing. He was one of the promoters of supergravity right at the beginning. And Bernard Julia really came to me a long time ago already to say that he has a contraindicated note in which he discusses the link between the Einstein equation, I mean really the condition for a metric to be Einstein, and some kind of linearization of the Rarita-Schwinger operator, I mean the tangent space to the solution of the equivalent of the harmonic spinors, which are spinors annihilated by Dirac. You can look at 3/2 spinors, which are annihilated by Rarita-Schwinger, and you can look at the tangent space to this and connect this to the moduli space of Einstein metrics. And I've been looking into that quite a bit without success, but maybe I think my point here again is that the idea of theoretical physicists, if something is important, I think mathematicians should take it seriously. Thank you very much. Happy birthday.
Is there a physical reason why 3/2 spinors are more important than 5/2 spinors or 7/2 spinors?
Well, because it's a fundamental state in some way. I mean, I think it's objects tend to be after that composite. So it's like looking at the hydrogen atom. If you look at atoms with more, I think there is a similarity of this nature. So, but I don't know why mathematicians have not been, after all, I mean, all these representations are interesting. If you look at tensors, you don't stop at vectors, you look at other tensors. And we know now that 3 forms are very interesting, and 4 forms could be also very interesting. So I don't see really any reason why we stop there. And although, as I said, I mean, if you work a little bit with the Rarita-Schwinger operator, it's not so nice. I think there are some papers where people, it becomes technical. So as usual, when you have technicalities coming up, you have to invent the formalism which makes the technicality forgettable.
Is there a special reason why to restrict it to 3/2 and to go to 5/2 and 7/2?
No. Well, my point in saying 3/2 is just you go to the next stage, and probably if you find a clever way of dealing with all of them at once, like the Banders of that was the idea of the Banders of Yuval Ne'eman. So he really wanted to put on a completely equal setting all the half spinors. That was his approach. So maybe the idea of singling out the 3/2 spinors is not a good idea. You have to take all the Banders at the same time. Maybe that's the right approach. So you have a point, yeah.
Okay, is there any other questions? Another question? Let's thank the speaker again.
Thank you.